proyek-proyek dari perusahaan multinasional milik pemerintah dan swasta. PT Multibangun Rekatama Patria selalu menjaga kualitas material dan pekerjaan dengan didukung oleh tim yang kompeten dan berpengalaman di bidangnya. Visi PT Multibangun Rekatama Patria adalah menjadi pemimpin pasar dalam industri geosintetik di Indonesia yang selalu bersaing dengan sehat. Misi PT Multibangun Rekatama Patria adalah menjalankan kegiatan perusahaan dengan standar etika yang tinggi dan bermartabat disertai dengan kejujuran dan integritas. Meningkatkan kesadaran pengguna produk geosintetik untuk memilih produk dan solusi yang tepat atas masalah proyek yang dihadapi. Menjual dan melakukan pemasangan produk-produk geosintetik yang berorientasi pada kepuasan pelanggan dengan memberikan pelayanan berupa material berkualitas dan jasa pemasangan oleh tenaga-tenaga ahli dan berpengalaman. Mengembangkan perusahaan dengan sumber daya yang modern dan profesional. Memberikan penghargaan kepada karyawan melalui kesejahteraan yang baik, penyediaan lingkungan kerja yang aman dan nyaman, serta kesempatan untuk mengembangkan karir. Produk-produk PT Multibangun Rekatama Patria. Produk Tensar System terdiri dari Geogrid Tri-X, terbuat dari bahan polipropilin berkualitas yang berfungsi sebagai stabilitas tanah dasar, khususnya pada tanah lunak. Multi-block retaining wall system. Multi-block retaining wall system merupakan sistem konstruksi dinding penahan tanah segmental, perpaduan antara modular blok beton sebagai facing dan tensar uniaxial geogrid sebagai perkuatan tanah. Geomembran. Geomembran terbuat dari polimer plastik yang bersifat kedap terhadap cairan. Kami juga menyediakan produk-produk geosintetik lainnya seperti geotekstil, material drainase, serta geosintetik clay liner yang menjadi solusi bagi proyek-proyek Anda. Gudang PT Multibangun Rekatama Patria hanya 5 menit dari gerbang tol Bitung Tangerang, sehingga memudahkan akses pengiriman material. Gudang PT Multibangun Rekatama Patria terletak di kawasan pergudangan pengembangan kawasan terpadu 2, Bitung Tangerang. Yang mempunyai luas 3.300 meter persegi yang dapat menampung material geosintetik dengan pengaturan dan penyusunan material yang tertata rapi. Serta pengoperasian alat dengan tenaga profesional. Kami pastikan material geosintetik tetap terjaga kualitasnya hingga sampai di lokasi proyek. Selalu ready stock dan pelayanan profesional adalah komitmen kami. Dengan pengalaman dan pelayanan yang teruji, maka jangan ragu untuk menghubungi kami. Kunjungi website kami di www.multibangunpatria.com.
Selamat pagi, salam sejahtera bagi kita semua. Kepada Bapak, Ibu, dan rekan-rekan mahasiswa sekalian, saya ucapkan selamat datang di acara MRP Webinar Series yang kedua dengan tema Measuring Soil Strength Using the Shear Box, Do's and Don'ts pada pagi hari ini, 16 Maret 2021. Webinar ini dipersembahkan oleh PT Multibangun Rekatama Patria, Geosintetik Spesialis. Sebelum memulai acara, perkenalkanlah saya membacakan susunan acara webinar pada pagi hari ini. Pertama, akan dibacakan tata tertib dan tata cara dalam webinar kami. Kedua, sambutan oleh Bapak Insinyur Nur Zaman selaku perwakilan dari PT Multibangun Rekatama Patria. Acara kemudian dilanjutkan dengan paparan oleh Bapak Michael Dobie, dilanjutkan dengan sesi tanya jawab. Sebelum mengakhiri acara, kami juga sudah menyiapkan kuis berhadiah untuk 3 orang pemenang. Maka dari itu, peserta dimohon tidak langsung meninggalkan webinar setelah paparan berakhir. Informasi terkait sertifikat dan lainnya akan diumumkan di akhir acara. Baiklah, demi kenyamanan bersama, saya akan bacakan terlebih dahulu tata tertib webinar pada pagi hari ini. Presentasi oleh pembicara akan dibawakan dalam bahasa Inggris. Apabila Anda memiliki pertanyaan untuk pembicara, dapat langsung diketikkan dari sekarang dan selama presentasi berlangsung melalui fitur Q&A yang terletak di bawah layar Anda. Pertanyaan dapat disampaikan dalam bahasa Indonesia, tapi akan lebih baik jika disampaikan dalam bahasa Inggris. Webinar ini juga disiarkan secara langsung di channel YouTube kami, yaitu Multibangun Rekatama Patria di link s.id/webinar MRP Live 2 atau yang kami share pada kolom chat. Untuk mempersingkat waktu, saya persilakan Bapak Insinyur Saman selaku perwakilan dari PT Multibangun Rekatama Patria untuk memberikan sambutan. Kepada Bapak Nur Zaman, dipersilakan.
Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi Bapak, Ibu, dan saudara sekalian. Kami ucapkan terima kasih atas kehadirannya di acara webinar Zoom kali ini. Perkenalkan, nama saya Nur Zaman, mewakili PT Multibangun Rekatama Patria, perusahaan yang sudah berpengalaman dalam bidang geosintetik spesialis sejak 1991. Kami berkomitmen penuh dalam mengembangkan kualitas dan juga aktif berpartisipasi dalam membangun negeri sesuai dengan bidang kami, seperti penyediaan material geogrid untuk infrastruktur jalan, perkuatan tanah lunak, jalan akses pelabuhan, pembangunan terminal peti kemas, perkuatan timbunan, dan juga penanganan longsor. Ada juga material geomembran untuk pembuatan kolam penampungan limbah ataupun air bersih, dan juga untuk landfill atau TPA. Kami berencana untuk secara rutin berbagi pengalaman yang berkaitan dengan bidang geosintetik dan juga geoteknik melalui webinar Zoom ini. Sharing webinar ini kami adakan sebagai bentuk kontribusi kami di dunia teknik sipil secara umum maupun bidang geoteknik secara khusus. Semoga webinar Zoom ini bisa memberikan manfaat yang semua. Sebagai penutup, jangan lupa bersyukur dan patuh pada protokol kesehatan 5M, yaitu memakai masker, mencuci tangan, menjaga jarak, menjauhi kerumunan, dan juga membatasi mobilisasi. Selamat mengikuti webinar. Terima kasih. Wassalamualaikum warahmatullahi wabarakatuh.
Terima kasih kepada Pak Nur Zaman atas sambutannya. Selanjutnya, webinar pada pagi hari ini yang bertemakan Measuring Soil Strength Using the Shear Box, Do's and Don'ts akan dibawakan oleh Bapak Michael Dobie yang merupakan Regional Manager Asia Pacific of Tensar. Sebelum beralih ke Bapak Michael Dobie, saya akan membacakan CV beliau. Bapak Michael Dobie telah menempuh kualifikasi akademiknya pada tahun 1973 di University of Bristol dengan gelar sarjana Bachelor of Science Civil Engineering dan melanjutkan di Imperial College London pada tahun 1977 dan berhasil meraih gelar Master of Science in Soil Mechanics under Profesor Bishop. Beliau mendapatkan gelar Professional Chartered Engineering UK pada tahun 1978 dan merupakan seorang fellow ICE di tahun 2011. Beliau juga mendapatkan Chartered in Station of Highway dan Transportasi pada tahun 1992. Bapak Michael Dobie memiliki pengalaman lebih dari 40 tahun di bidang geotechnical engineering di Inggris dan di luar negeri, terutama yang berhubungan dengan jalan raya, perumahan, jembatan, dan dermaga. Baiklah, sekali lagi saya ingatkan kepada Bapak dan Ibu yang memiliki pertanyaan untuk Bapak Michael Dobie, bisa langsung menggunakan fitur Q&A yang terletak di bawah layar Anda. Pertanyaan dapat disampaikan dalam bahasa Indonesia, namun akan lebih baik jika disampaikan dalam bahasa Inggris. Tanpa memperpanjang waktu, kepada Bapak Michael Dobie, the time is yours. Silakan, Pak.
Okay, good morning, everybody. I am pretty sure that I am now sharing my screen and I hope you can hear me. First of all, I'd like to thank you all for attending our MRP webinar today. It's very nice to see so many people joining in. I'd also like to thank very much PT Multibangun Rikatama Patria for organizing this. They do a huge amount of work behind the scene. I just turn up here and present my material, but a lot of work is done to create these webinars. And especially I'd like to thank Weera for the very nice introduction she just gave us. So I now need to get on with the presentation material. You've heard about the fact you can ask questions and so on. So let's see how we get on, and off we go. So the topic today is about measuring soil shear strength using the shear box. And I said do's and don'ts. And I hope that'll become clear as to why I have that title as we go along. This is actually the second in a series of webinars on the topic of geotechnical engineering that PT Multibangun have organized. And as I said, we're going to look at measuring soil shear strength using the shear box. And in this particular case, we're only interested in the soil strength in terms of effective stress. And we normally refer to these with the parameters C' and Phi'. And we would need these to carry out designs of almost any kind of earth structure, reinforced soil structure, slope, etc. So they are very important parameters. And in this particular case, principally, I'm looking at using these materials as fills. The next webinar, which will be next month, we shall move on a bit further and look at the principle of effective stress. And then we shall also look at measuring soil shear strength using the triaxial test. That'll be the next webinar. So there's a brief outline of the webinars we plan. We're now on the second one. And the other titles there may change slightly as I go along and we see how the material is working out. But certainly the April one will be as given in this list. A few little images, a small shear box. And the small shear box set up, ready for action. It's a nice clean picture, probably taken from a catalog. So the equipment looks very nice. And this is a large shear box. This one will be 300 millimeters by 300 millimeters. And it's pretty heavy. You can't pick that up by yourself. So you need all sorts of equipment to lift it. And here it is in position, ready for carrying out a test. And what we need to remember in the whole of this discussion today is that what we're trying to find out is the shear resistance in terms of effective stress on a particular plane. Now, of course, in a shear box, the plane is created by the action of shearing in the middle of the shear box. We know that. Is that a bad thing? Well, not at all. It actually gives us a very good indication of shear strength. And that, I think that's why this test gets used so much. And I think the reason why I have made this our second webinar topic is that when I look at geotechnical reports from Indonesia and many other places, the shear box is frequently being used to determine the strength parameters for fills. So it is therefore an important test. So who is it intended for, this webinar? And well, the aim here is really to supplement existing standards and codes of practice. And what I tell you is going to be based on an extensive experience of both carrying out and reviewing data from shear box tests. And perhaps one target is to create some kind of checklist of features and test conditions which you should look at when you are reviewing results. Now, as we go through this presentation or this webinar, please look out for these little blue boxes, which will pop out quite a lot because they are providing additional information and they are also posing a few questions as well. And you've already heard that there will be some 3 questions at the end of the webinar, and maybe there will be some clues in these blue boxes. So the material is aimed at civil engineers in general who have some involvement in ground engineering, which is all civil engineers really. And it might be of interest to more experienced geotechnical engineers, but the main target is looking at the strength properties of fills, in particular for reinforced soil applications, because that's the field that we work in. And of course, this is vital information when you're looking at the design of these structures. I think in particular, it's like this. I'm sure many of you will receive reports, maybe from site investigation contractors, and you'll get tables of values like the one you see there. And maybe at the end of this table, there'll be a couple of columns there where you see some shear box test results, C' and Phi'. And the question then is, should you just use those values directly? Should you just take them out of the report and put them straight into your slope stability program or your finite element analysis software? Or should you maybe have a bit of a look first and make sure that these properties are suitable for the task that you're going to use them for? And I think you'll realize immediately that my answer to that question would be yes, of course you should. Some important standards I'm going to refer to a bit today. The ASTM, which is reference D3080, is for this particular test. In particular, it is for consolidated drained testing conditions, which is very important. And then there is an SNI 2813, which has the same basic title, but of course in Bahasa Indonesia. It's actually interesting that the ASTM D3080 has officially been withdrawn if you look at the website. But however, it's still an extremely good document. I think of the codes I'm aware of, it's certainly one of the best. But I see no plan yet for what they're going to do to replace it. But anyhow, that is the situation with that one. As regards any books or reading, well, this was published many, many years ago. It's a series of 3 books published by Ken Head, and volume 2 covers tests like the shear box. It's probably a bit old fashioned now in some regards, but the basic information in there is extremely useful. And I certainly went back to this to help me with the preparation of some of the material in this webinar today. Now you might say, wow, 1 hour on the shear box test. Oh my gosh. Well, I'd have to say that there's a lot to cover, and actually 1 hour may not actually be long enough, but I need to go quite quickly through this to give you some chance to ask questions and so forth at the end. But we're certainly going to look at the main issues with shear box and try and understand what you should do and what you should not be doing, and how to interpret information when you see it in reports. So the content is like this. We'll first of all, to kind of warm ourselves up, look at a typical shear box test result on dry sand, which is very straightforward conditions. And then I'm going to review 3 important issues which you need to think about when you look at shear box test results: scale effects, things to do with pore water pressure, and also relating your results to a general shear strength model. I will then look at test procedures or suggestions for various typical soil types. And finally, we'll look at verification of strength values using index tests. It's a vital final step. So when you have results from, say, a shear box test or even a triaxial test, it's a very, very good idea to relate them to index properties for the soil and make sure that you get a good correspondence between the two. And you've already heard at the end, there will be a quiz. There are 3 questions, and they are based on the material presented in this webinar, and there are some prizes for the winners. So let's look at this shear box test on dry sand. With any test, there's always going to be information you'd like to know about it. Now, I'm not going to read through all of that there because we're going to come back to it as we look at the results. But you'll see there, if you want to read it as I'm talking, information about the grading, the compaction condition, the size of the shear box, etc., etc. So let's actually look at the test in detail. Before we do that, here's a particle size distribution curve for the sand that's being tested. It's a FM sand, fine to medium sand. And I've also put there a red dotted line, which indicates the maximum particle size that will be tested on this particular occasion. So in this case, it's a very nice result because almost all of the material will be used for the shear box test. And then I have this little kind of animation of how the test works. So we have 2 graphs on the left. The upper one is going to show us shear stress, which is coming from S on the diagram, versus the horizontal displacement, that's delta H. And the lower diagram is delta V, that's the vertical movement of the shear box, also against the horizontal movement. And we're going to see a first test where we apply a normal load, which is represented by, in this case, by a particular stress there of 97.1 kilopascals. And we start the test. So we start to increase S. And if you watch carefully, when we first start, the shear box both goes horizontally and upwards. And you can see the upwards movement in the diagram at the bottom. And we call this dilation. And this is a very, very important aspect and feature of shearing, especially in granular soils like this. Anyhow, we reach a peak value of the shear stress. We carry on shearing a bit further. The shear box starts to move purely horizontally, which we can also confirm in the lower diagram. So we see quite nicely from that animation how we expect the test to run. We normally do this at several different normal stresses. There are 3 of them in this case. Then having done that, we then draw an additional diagram that looks like this, where we look at, in this case, the peak shear stress values for each of those tests, and we plot it against the normal stress values. And you've got 3 dotted points there, and we draw a line on that, which in this case I've taken down through the 0, 0 point, and we measure that angle, and in this case we're going to call it phi peak, because it's taken from the peak shear stresses. However, there is an alternative interpretation of this data, which is to take the shear stress from the point in the test where the shear box is traveling horizontally. In other words, its volume is no longer changing. And this one we normally call the phi dashed at constant volume, phi dash CV. And of course, it's going to be a lower value. And if I summarize all of that with actual numbers, you see the values there. This would be very typical for a fairly angular, well-compacted sand. So there is our typical result. And what I'm going to do with this, I'm going to add a little table of information on the bottom right. And there are 5 items in here, which I'm going to read through to you this time, but you're going to see this repeated several times in different examples of test results. Shear box size, in this case, 100 millimeters. That's both the width and the length of it. Maximum particle size tested was 3.3 millimeters. it was tested and prepared in a dry condition. The rate of shearing was quite fast. It's 0.8 of a millimeter per minute. And some kind of information about the density or the compaction condition of the soil, in this case, 98% of the maximum dry density. And if you like, this information that you see now is really what you need as a minimum to be able to review a shear box test. And you'll see as we go along, you're going to see this layout of information quite a few times for different results. And you're going to see in some cases bits are missing. But on purpose, I leave all of the items here. And sometimes, I mean, frequently you'll see the vertical movement of the shear box missing in a test, which is a great shame because that is very helpful to help you interpret the results you're seeing. Also, something you will sometimes see in shear box test reports is that the horizontal axis is quoted as strain in percent, horizontal strain. Please realize that this is incorrect. There is no strain measured in a shear box test. It's simply horizontal displacement. Sometimes it's given as relative displacement, in other words, displacement compared to the width of the shear box, but there's no point in doing that. It's far best just to look at it in displacement in millimeters or centimeters or whatever you're used to looking at. Now, let's look at the first of the three items I want to talk about, scale effects. And to do this, I'm going to make use of my colleague Andrew Lee's coffee mug. And his coffee mug, ground coffee, it's about 75 millimeters high. So if I put a large shear box nearby, it looks like this. So to scale, that would be the size of a large shear box. We saw it earlier on in the pictures with the dimensions given to you there. Whereas the standard, or I'm going to call it small shear box in this case, is normally 60 millimeters across, 20 millimeters high. And there it's drawn to the same scale. And you can see that they look very different when you look at them in that way. We'll put some dimensions on there, H for height and L and W for the plan dimensions. And then one other important piece of information is the maximum particle size, Dmax, that we're going to test in the shear box. Now, if we look at ASTM, it has these requirements. I won't read them to you. You can see them there, but it has those requirements as a limitation on the maximum particle size. So if I actually put that into the shear box, it'll be 25 millimeters in the big shear box or large one, and it would be 3.3 millimeters in the small shear box. And I've drawn the particles to scale. But if you look further into the literature, you'll find some information published by two very well-known people, Joule and Roth. This is going back to 1987. And they were requiring that ratio, L over D max, should be greater than 50 to get a representative result. Now, if I change to that requirement, then my particles shrink down to 6 millimeters and 1.2 are still drawn to scale. So this is actually quite a nice way of getting an idea about what the particle size might look like compared to the size of the shear box. And of course, the dotted line in the middle will be the shear plane where the shearing will take place. One other point to make about this is the volume of soil in each type of shear box. So if we take the ground coffee mug again, we need about 1/3 of a cup to fill the small shear box. And really, this should be used only for fine soils and sands. And then for the large shear box, you need 64 cups. And this one would be okay up to about the medium gravel size. We will come back to those particular requirements a little bit later on, but there we are, we have them, the scale effects. Now, if you want to look at the practical application of these scale effects, this is some very interesting testing of two soil types. So now on my particle size curve, I've got a red colored river sand, which is non-plastic and no fines. And we got a well-graded gravel starting at large sizes and going all the way down to fines. They're really two very different soils, and the gravel has plastic fines. So it's been given a liquid limit and a plasticity index. Let's look at the results of these. So I'm going to use my same basic layout. So this layout we've seen already. I don't need to describe it to you in detail now, but you can see there now, for example, shear box size 300 millimeters, maximum particle size tested 2 millimeters. And in this case, the test condition is damp, rate of shearing fast, and you've got information on the unit weight and water content. But what you'll see there is that the results, first of all, the horizontal displacement has much bigger numbers now because it's a large shear box, but the peak values are reached relatively quickly. So that is for the river sand. And these are the different vertical normal stresses. If I now superimpose on that diagram the results for the gravel, they look like this. And what you'll see then is to reach peak values of shear stress, you have to travel quite a long way with the shear box before you reach there, over 40 millimeters. So therefore, it's quite clearly obvious you need a large shear box to capture the shear strength behavior, and that's only the peak strength. If you compact the same gravel to a denser condition, then what you'll see has happened is that you reach the peak values more quickly because the gravel is denser. However, you still have to travel with your shear box quite a long way to reach those peak conditions. So this is a very nice illustration of the importance of shear box size on different soil types. The next thing is about ensuring that water pressure is zero. Now, when we interpret shear box test results, we're going to use the more Coulomb equation or relationship, which is given to you there, but the shear strength equaling C dashed plus the effective stress sigma dash times tan of phi dash. But we never know what is sigma dashed. So we have to write it down as its two components. That's to say total stress and pore water pressure. Now, we know the total stress because that comes from the normal load. That is a total load, so it gives us a total stress. But then the big question is, what is the pore pressure? And this is a really important question, especially in the finer soils. Now, in the shear box, unless you've got some very sophisticated equipment, which I'm not very familiar with, but we cannot measure the pore pressure, not in the standard equipment. So what we have to do is to carry out testing to make sure that this U, this pore pressure, is either zero or very small indeed. Now, one way to do this is to test dry, which is what we saw in that first example. In other words, the soil is dry and also the shear box is dry, no water at all. Then another test condition that is frequently occurring is when the soil is tested, and I'm calling it damp. And in this case, this means that almost certainly the soil has had water added to it for compaction. But in the test procedure, the box is left dry. So so the soil stays damp. Now, this can lead to great uncertainty about the U value, especially if you have a high fines content in the soil. So what we normally do to overcome this is we need to saturate the soil. And the way we normally do this is by flooding the shear box. We fill up the surrounding part with water, and that water is able to communicate. What's really important, it can communicate with the water inside the sample. So this gives a way for the soil inside the shear box to reach a stable water pressure of around about zero. Please realize that this does not mean that we're implying that the soil is going to be saturated when we use it as a fill. It almost certainly won't be. It's simply being done to make sure we know what is U. Then the third of these important things is looking at a general shear strength model and comparing our results to this model. Now, this particular one I've taken from an old British standard, the one for retaining walls, but it's a very nice model, and you'll come across this kind of idea in many other places. But you'll see there the same basic shear results that we've seen from the shear box tests. But what you will see is that the shear strength envelope, in other words, shear stress versus normal stress, has got two parts to it. It's got a peak strength, which is the darker color, which is curved, and we've got a constant volume strength, which is the lighter color, and that is a uniform linear straight line. And the region over which we get this curvature is the region over which the soil is over-consolidated. In other words, it's had a previous high pressure applied and then removed. And that's why we get this kind of behavior. So the normal envelope, especially in the peak area, is not necessarily a straight line. It might look like one, but it's going to be curved if you get the complete behavior. This becomes a bit more difficult when we move to clays, especially with a high PI, because with high plasticity index clays, we tend to find behavior changing. And we find that the shear stress goes past peak and goes past constant volume and heads down to something that we call residual shear strength. And I've changed the horizontal displacement scale to do this. So what we're looking at there is the behavior of a clay when you have shearing over a long distance, which is the picture I showed you earlier on, but that's London clay. London clay has a residual phi value about 8 degrees, 8 or 9 degrees, which is very low, of course. But this is an important thing to be aware of when you are reviewing the results from shear box tests. So I thought before leaving this, I thought I'd just take one particular point. Let's go back to this diagram, and I'm going to put on here 3 possible results from shear box tests. There they are, the red squares. Now, if I simply put that result, say, into Excel, and I add a trend line, the trend line looks like this. And the trend line is suggesting that we have a very high C dashed. And this would be rather dangerous because at low strengths, or low stresses rather, you're going to overpredict the shear strength. So we need to be very careful about this kind of interpretation when we look at shear box results. Please be aware that C dashed, as you see it there, is coming from a backward extrapolation of the data. It's not actually being measured. And of course, how can it be over-consolidated? Well, this is also induced by compaction. So when we compact to fill into the shear box, this effectively is over-consolidating it. So what I want to do now is to run through a number of different soil types and discuss some of the important issues of their testing. There are lots of words here, and I'm not going to read all of them. I put in bold some of the important words, but the reason for having so many words is that when you receive this, this presentation as a handout, you will have this fairly complete information available. So start with the fine soils, clays and silts. We can definitely use the small or standard shear box because there are no scale effects. But the big issue is pore water pressure and making sure that it is either zero or negligible, thinking back to that previous slide a few minutes ago. Pore pressure in a clay will react to the loading, both the normal load and the shear stress. And it's vital that test procedures should make sure that we keep the excess pore water pressure as low as possible. And this is going to require 3 stages: saturation, consolidation, and shearing. And this can take a long time, easily 24 hours per item. So that means 1 test, 3 days, 3 samples, 9 days. So this kind of test procedure is likely to be relatively expensive. Let me just explain what I mean by some of this. So let's look at setting up a test. So we prepare our sample in the shear box, and we normally apply a small normal load just to hold it in position. And then we fill the shear box with water, and we will leave it for at least normally 24 hours until, and you'll see, I hope by the coloring, the sample becomes saturated. Now, you won't get it fully saturated. You can't drive out all the air, especially from a fine soil. But the important thing is you have a good connection between pore water in the sample and the water outside in the shear box. So that's the saturation stage of the test. We now apply the full load, big N, and we then plot a curve or a graph of the vertical settlement versus root time. And here could be a typical example. You can also plot against log time. There are two ways. It's like a consolidation test, but we're generally going to pick out one of 3 times, either for 50% consolidation, 90%, or 100%. It depends on the code of practice you're looking at. And this is, of course, is the consolidation stage of the test. So having identified either T50 or T90 or T100, we then calculate the required time to failure in the shear stage of the test, and we take it as either of 50 times T50, 11.6 times T90, or 12.7 times T100. Now, it doesn't really matter which one you use because they're going to give you much the same result. Once we've done that, we then have to make an estimate of our displacement at failure, which we probably know after we've done a few tests accurately. To begin with, you can guess it. And then from that, we calculate the rate of shear, rate of displacement, which equals dF over TF. So quick example. Imagine we do the test and our T50 is 10 minutes, quite likely for a clay material. So our time to failure, TF, should be 500 minutes. And if we estimate that DF is going to occur after 5 millimeters of movement, then our rate of shearing or rate of displacement should be 5 over 500, which is 0.01 millimeters per minute, which is very slow. It'll take about 24 hours to do the shearing under those conditions. A word of warning here about the Indonesian standard SNI 2813, because there appears to be an error in section 711 where the TF value is given directly as T50. In other words, this formula here in the SNI doesn't have the 50 in it. It just says TF should equal T50. Now, if you follow that procedure, then your shearing is going to be 50 times too fast, which is not a good idea, as you're going to see later on in some of the examples. Anyhow, having calculated that rate of shearing, RD, or the rate of displacement, RD, we then apply the shear force and the rate of movement of the shear blocks. It's a displacement control test, will be given by RD, calculated from the consolidation stage. So that's the shearing stage of the test. So let's look at a nice result here. So this is a test on a fine sandy clay. It's pretty complete. We have the box size, it's a small shear box, maximum size is fine sand. It was done saturated. That means both the sample and the shear box full of water. And if you look at there, the rate of shearing, it's a really slow 0.0072 millimeters per minute. So this is a very nice demonstration that you can get extremely nice looking effective stress parameters out of the shear box test, providing you do it slowly in the case of clays. Okay, nice test. Here's another one. These are some tests on silty desert soils. They're low PI, and they're classified in AASHTO as A27 soils, so that should tell you something about them. And what we see here, a reported shear strength of C equals 41 and phi equals 22. Now, what do you think about that? Well, let's have a look at the information. It's it's a 100 millimeter shear box, only got fine, so there's no problem with scale effects. But the test was done damp, in other words, not flooded, at a rate of shearing of 0.8 millimeters per minute, so very fast. So what this means is we have concerns about the pore pressure inside the shear box. And in fact, this is a very good example of something that I've actually given a special name to. I call it a high C, low phi result. And I see it many, many times. And it's coming from testing fine soils, clays or silts, in the shear box at very high shearing rates like this. Now, if you are confronted with that result, I'd suggest you simply reject it. You cannot use it for design. It doesn't make sense. However, your client or the consulting engineer might not be very happy if you simply reject it. So what you should first of all do is investigate the result and find out the reason for that kind of behavior. Now, the explanation is like this. Let's just imagine this particular soil has a C dashed of 0 and a phi dash of 27 degrees. And I draw that line on the same diagram. So the horizontal distance between those points is therefore suction in the sample. So it's the suction that's giving us the high C, low phi result. So please be aware of that. But do not reject out of hand. Please investigate first before you do so to make sure you understand why you have that kind of behavior. But here's a bit of a problem, because these are some published test standards for the shear box for clay soils. And there are 3 of them. First one, and I'll read through them quickly. Slow shear test for clay soil, rate of shear less than 0.02 millimeters per minute, or time to failure greater than 50 times T50 from the consolidation test. Exactly what I've just been talking about. So perfect for carrying out this kind of testing. Second one, consolidated fast shear test for clay soil, rate of shear 0.8 millimeters per minute. And the third one, unconsolidated fast shear test for clay soil, rate also 0.8 millimeters per minute. The second 2, T0141 and T0142, are pointless. The data you get from those will be something like the previous example. They do not provide meaningful shear strength parameters, certainly not C dash and phi dashed. So please avoid those sorts of test procedures. And if you find tests are carried out following them, please be very suspicious of the results and carefully review, as we did in that last example. Here is some data from a fill soil in Indonesia. Lots of nice data there, all the information we'd like to know. Unconfined test towards the bottom, and it's got some quite high values, so it's quite a stiff clay. And we got C and phi. And what do we see? High C, low phi. But if we look at that particular SNI standard there, then it is for an unconsolidated fast shear test. And therefore it gives high C, low phi. Let's move on now to the next type of soil, sands with high fines content. Now we can use the standard or small shear box. That's okay, because we're not going beyond the sand size. But the problem is with a high fines content, then you may run into similar problems as we see with the clays and silts when it comes to the issue of pore pressure. Therefore, we also need to be careful about the rate of shearing, but unfortunately in these sorts of soils, sometimes it's difficult to measure T50 or T90. But luckily, the ASTM gives some very useful guidance about suggested times of failure you can guess or estimate for this kind of soil. And it says TF should be assumed to be greater than 60 minutes if the fines are more than 5%, and greater than 200 minutes in the case of a clay sand. And that's really useful guidance, and I'd suggest you keep an eye on that one when you're looking at planning this kind of testing. As a general rule, slower is better. If you're not sure, test more slowly. Move on to clean sands. Clean sands with negligible fines, very much like the very first example I showed you. Again, the standard shear box is normally okay as long as we stay in the sand sizes only, so minimal scale effects. And you can test them dry if you can achieve adequate density. High displacement rate is no problem if they're dry. But if you decide you need to add water and flood the shear box, then again, you may have to be a wee bit more careful about the rate of shearing. And again, ASTM suggests that T to failure should certainly be greater than 10 minutes when fines are even less than 5%. So that's a good piece of advice there. So here is a very nice test result. This is on a fine to medium sand, similar to the one we saw earlier on, in non-plastic, and it's compacted to a very dense condition in the 60 millimeter shear box, dry, and a fast test. Very nice result, very clear dilation, very clear peak values, and a very clear constant volume behavior. What was interesting in this case is that the same sand was tested in a loose condition, which is the open dots. So first of all, you'll see there's no dilation. The vertical displacement is only downwards. So the soil is becoming compacted as you shear it. And there's absolutely no sign of a peak, but all the results end up at roughly the same constant volume condition. And I think what's so nice about this test result, it shows you so clearly the dependence of phi peak on the compacted density. So you could imagine at a range of, in this case, the density is given by its void ratio, but at a range of void ratios between 0.42 and 0.61, you could have a significant range of phi peak values. So if you're using this sand to build a structure, you've got to be very confident about the likely compacted condition when you choose the phi value for design. Let's move on to clean gravels. Clean gravels, you've got to use a large shear box, again, to minimize any scale effects. And there is going to be an issue about maximum particle size. Now, if you follow ASTM, you can go up to 30 millimeters, but I think it's a bit big. According to Joule and Roth, you shouldn't go beyond 6 millimeters. Probably somewhere in the range of 10 to 15 millimeters would be about right. And this, of course, means that in many cases, you're going to have to remove coarser particles. But again, as with the sand, if you can get adequate compaction or density, then you might consider testing it dry. So I'm just going to show you a result here. This is for a crushed gravel. So these are nice angular particles, well graded. This is the purple colored material. I've superimposed it on the grading curves from the previous examples we looked at. And I've also added there, just to mention those dotted lines, the 75 micron limit, where we normally say the fines start below that value, and 4 to 5 microns, if you remember from our previous webinar, because below that value, that's the value we use, that's the material we use to do the Atterberg limits. This one turns out to be non-plastic. And here are the results. So jumping straight in, you'll see again, quite large horizontal displacements up to 40 millimeters because it's a large shear box, well-defined peak values and a well-defined constant volume behavior. So this is a particularly nice example. You'll see maximum particle size there is 14 millimeters and it was done saturated. But despite that, it was also tested quite quickly. So the testers were happy that it could be tested quickly, even though it was saturated. So it's a really excellent shear box test on crushed gravel, and it's giving the kind of phi peak and phi CV you would expect from a material like that. Now here's a topic which I think is quite important, is what I call testing the wrong soil. So here is a soil. It's a well-graded sandy gravel with a bit of fines in it. And you get a result back, and the result looks like this. Unfortunately, there's lots of information missing, but as I said, I still show everything because, or what should be there to remind us, but lots of things are missing. We've only got the peak shear stresses, and we get a phi of 35 degrees, which, well, it's not bad. But when we look carefully, we see 60 millimeter shear box, maximum particle size tested, 2 millimeters, saturated, quite fast shearing, and it was well compacted. So what about this? This means we're testing a material that's a gravel, but only up to the 2 millimeter particle size. So if we go back to the particle size curve and we remove the coarse particles, we end up testing what is essentially a fairly well-graded sand with a fairly high fines content, far away from the actual material. So we saved some money on a cheaper test, but we lost maybe 6 or 7 degrees on our phi value. And if you were designing a big retaining wall, for example, that could cost a lot of money because the difference, a difference of 6 or 7 degrees in phi would have a big effect on a retaining wall design. So do not rely on small shear box testing of gravels when you're serious about getting a representative value of phi dashed. Gravels with high fines content. Now these really represent some of the most difficult soils to test. The reason is that the coarse fraction will probably dominate the shear strength behavior, but the fines and the fine sand will probably fill up the voids and then dominate the pore water pressure response. And this is difficult. So we really do need to saturate, but then we get worried about the situation with creation of suction on shearing. I'll show you a little picture of that in a minute. And if that'll happen if you test very quickly. But the problem is with a large shear box, if you go through the full saturation, consolidation, and shearing procedure, then the duration of the test could be extremely long. And to be honest, people would rarely do it. So what do? Well, I think these soils are difficult. But one possibility is if you're satisfied that the coarse particles will dominate the shear strength behavior, is to actually do the test dry. You might have to remove some of the fines, otherwise it would go hard, it would kind of set inside the voids, but you could test them dry. It's a possibility, but it's a judgment you have to make when you're testing this kind of soil. This is the issue. So we're now looking at a large shear box, and we got two particles at roughly the right size in terms of their scale sitting there, and we start to shear it. And due to dilation, the shear box goes up. Now that dilation will tend to create a lot of suction in the finer soils within the pore spaces. And that is a problem on the shear plane. So this is why I want to highlight that particular issue in carrying out shear box testing. Here's a rather interesting test. When you first look at this one, it doesn't look bad, but it is a test on gravel and it's got some plastic fines. And when we look at the shear stress versus horizontal displacement graph, they look quite good. You've got some peaks and they drop down to lower values. But when we look at the details, it's a 60 millimeter shear box testing a gravel carried out damp with a fast rate of displacement, fairly well compacted. So you have to be somewhat curious and suspicious about a test like this. If, for example, you put a straight line on the peak strength values, you're going to predict a very high C-dashed, maybe 50 or 60 kPa, which is simply not reliable. Another thing that's very interesting here, you can see a red line on the lower left diagram. This is the rate of dilation, which is an amazing 3.3. What does that mean? It means that for every millimeter the shear box goes horizontally, it moves upwards 3.3 millimeters. It's going up a really steep hill. Difficult to imagine how that can happen. So you have to be a bit suspicious of this test. And you'd have to be very careful how you interpret it. So really, if you put gravels in small shear box, you're going to get some unusual or strange looking results. Then the last soil, just to mention quickly, are what I'm calling mixed or gap graded soils. Now these may not be as difficult as you think. And there are two main approaches. So if you have a gap graded soil in which the coarse particles dominate the grading, so you're going to have coarse particle rubbing on coarse particle to give you shear resistance, then you could just test them as gravels with a high fines content, and maybe even consider going dry and removing some of the fine material. But you've got to be careful. If fine particles dominate, so in other words, if you've got coarse particles in a matrix of, say, silty clay, like many glacial tills, which we don't have in Indonesia, but we have in other places, then probably the best thing to do then is to remove the coarse particles and test it as a silty clay in the standard shear box, and then follow all the normal saturation, consolidation, and slow shear procedure. I've got no pictures for that. Last things to mention, what about procedures for verifying? I mentioned this is really important. Having measured strength, then you need to use index tests to verify that your values are reasonable. And this particular little technique, which is actually published now in two of the recent British standards, which have been brought into line with Eurocode, it gives you a very simple technique. So you've got two little equations there. This is for granular soils only, where it says that the phi-CV can be taken as equal to 30 plus two more terms, phi based on angularity, or an extra bit of phi based on particle size distribution. The K there means characteristic in Eurocode parlance. And then phi peak is the same, except we add on an additional bit, phi for dilation. And then these tables give you the range of these additional bits of phi value that you can add on. So in terms of angularity, between 0 and 4 degrees that you add on, ranging from rounded to angular. When it comes to particle size, again, ranging from 2 to 4, as you go from uniform, which is to say single size material, all the way up to well graded, with some special recommendations there on gap graded soils. So for this, of course, you need to look at your particle size distribution curve. Okay, so that's dealt with the first two. What about dilation? Well, this one, in this particular recommendation, is really looking at in situ soils, and it's basing dilation on what's called the density index, which can be related to the SPT result, for example. In terms of compacted soils, you'd have to try and make this assessment in a different way. But just to show you what it looks like, let's go back to this test result. Dilation is the difference between phi peak and phi CV, and you can see over on the top right diagram, it's just over 8 degrees. Another way to look at that is to look at the inclined part of that diagram bottom left. And this one has, well, this is the rate of dilation, which in this case is 0.176. And then we can use that to calculate dilation angle, which equals B times tan to the -1 of that value. And for sands, we would normally take B around about 0.8, giving us 8 degrees, which agrees very nicely with the graph above. Would you use 8 degrees for design? You have to make that judgment. Probably not, because you struggle to guarantee that you're going to have such a huge dilation everywhere at the same time during, say, the development of a shear plane within a structure. So I'm not talking today about how you interpret. I'm just talking to you about the data which you need to have to do it. What about fine soils? Well, if you go into the literature, there are many published correlations for phi dashed, normally with the plasticity data. Now, this graph you see here is a really elegant one. It's a very nice application of the Atterberg limits, where we are relating both peak and residual shear strength. You can see there the brown and the bluish colored dots to the distance, well, to the distance above or below the A line. And I'll explain to you what I mean by that in a minute. This is actually work published by Dr. Laurie Wesley, who I'm sure many of you will have heard about, especially as I mentioned him in our last webinar with his books. But this is a very nice relationship, and I think it's a very useful one to take into account. The extreme ends of the distance above and below the A line are into some very unusual soil types. Let's not worry about those too much. But the ones closer are useful. So but it's like this. There is a typical Atterberg limit diagram and plasticity chart. So we were talking about distance above the A line, that little blue arrow, or distance below the A line. That's what that meant in the horizontal axis of that previous diagram. Very useful. Here's some more published data. These are results from various sources plotting phi dashed for clays and clay silts against the plasticity index. And you can see how in general terms, especially for the peak values, they reduce as the PI increases. And that's coming from various sources. Please be aware that in many cases, these correlations will have been derived from alluvial soils. So they may not apply to the residual soils which we have here in Indonesia. So from that, I developed this little table. It's just a suggestion where we might look at the PI, see whether we're above or below the A line to give us some indication of likely phi peak or phi CV for design of an earth structure. And normally for fills, we're going to assume that C dashed equals 0. Some codes permit you to use a small value, but many codes would recommend for fills in particular, you keep C dash to 0. And I think that's the wise advice. Sometimes for very plastic soils, we might go a little bit, but maximum will probably be about 5 kPa. So if I take my recommendations and I go back to this graph and I plot them on there, they are the little straight lines with the circular symbols. So that's the recommendations for above the A line, the lower values, and this would be where the recommendations would be for below the A line. This is just my own ideas. You won't find those published anywhere else, but they seem to fit the typical ranges of data that we see from these correlations. But just one more reminder about the fact alluvial soils, mainly for alluvial soils, and probably glacial soils. So, a few conclusions and suggestions. First of all, the shear box, although many people say it has all sorts of problems, and the triaxial test should be greatly preferred, it's still a really good test, especially for when we're recompacting fills, which can be very difficult to do with triaxial testing. And we can get very good values of C dash and phi dash for a wide range of soil types, providing we carry out the test following the sorts of guidance I've been talking about in this webinar. It has the advantage of being very simple. It's a simple test. We don't require the sophistication of what's called the effective stress laboratory. Those of you who are familiar with or been to soil testing laboratories, normally there's a special room called the effective stress laboratory, and it's full of computers and all sorts of pressure control equipment and very complicated looking triaxial cells. And we don't need that for the shear box. The next webinar will be to talk more about what happens in the effective stress laboratory. But in the case of the shear box, it's not normally in that laboratory. It'll only be outside in a different area in most labs. For coarse soils, the main thing you need to think about is the scale effect, so that the maximum particle size you test should be related to the size of the shear box. And again, the standard or small shear box really shouldn't go beyond the sand size. And the large one, assuming it's 300 millimeters, should not really go beyond medium gravel, certainly not into coarse gravel. For fine soils, here the main problem is to do with the pore pressure issue on the shear plane when you're shearing the sample. And you've got to try to make sure it remains either 0 or very small. And this has got to be controlled very carefully by the full testing procedure, saturation, consolidation, and slow shearing. And we need to base that rate of shearing on the consolidation stage, which we saw in detail earlier on. As I said before, if in doubt, slower is better. And the other thing to do is to be on the lookout for what I call the high C, low phi results, and have a very careful look to see why you're getting them. I suggest when you're reviewing shear box tests, you can make a simple checklist, which can really follow the diagrams I've been showing you many times, to make sure you've checked shear box size, particle size, etc., etc. How is it tested? And so on. The rate of shearing, really important. And also, finally, I would always recommend that you verify the results you see from shear box testing against index properties, as we've just looked at briefly in the previous slides. So, I mentioned there a couple of the references which I used, which were both on scale effects. I used. There are probably some more references which I shall add to the PDF version of this webinar presentation, which you will be able to receive very soon. So I'll need a few minutes to do that, but then I'll add a few more references which are helpful to that list. So this will be our next webinar. Will be on the principle of effective stress and measuring soil strength using the triaxial test. In the meantime, thank you very much for listening, and I will do my best to answer any questions that you might have.
Terima kasih kepada Bapak Michael Dobie atas paparannya. Sambil memberikan waktu kepada Pak Michael Dobie untuk membaca pertanyaan yang sudah masuk, saya ingatkan kembali, Anda yang memiliki pertanyaan dapat bisa langsung disampaikan melalui fitur Q&A yang terletak di bawah layar Anda. Pertanyaan dipersilakan untuk disampaikan dalam bahasa Indonesia maupun bahasa Inggris. Selain itu, kami mengajak Bapak, Ibu, dan teman-teman yang hadir di sini untuk mengikuti berita dan informasi terkini seputar PT Multibangun Rekatama Patria dan MRP Webinar Series yang akan datang di bulan depan dengan follow dan like media sosial kami yang tertera di layar Anda. Follow Instagram kami di @multibangunrekataMapatria, Twitter kami di @multibangunrp, Facebook dan LinkedIn kami dengan nama PT Multibangun Rekatama Patria. Dan kami juga hadir di TikTok dengan username @multibangunpatria. Baik, Pak Mike, apakah sudah siap? Pertanyaan.
Okay, yes. Can you still hear me?
Yeah.
Okay, right. I've had a quick look at the questions, and actually people have made it easier for me on the whole, because I think almost all are in Bahasa Inggris. Yes, my gosh. No, there's one there. We'll come to that. Okay, so there are currently 9 questions, so I'll just take them from the top and go through them. I think we have time. First question is, how do we decide to use shear box testing over other shear tests? Good question. If possible, generally for the strength of soils, we would prefer to use the triaxial test. The triaxial test is fundamentally and theoretically a far more satisfactory test. However, when it comes to compacted fills, especially coarse materials, the shear box becomes very difficult to use. Sorry, the triaxial test becomes difficult to use. And that's a time when switching over to shear box can make a lot of sense. If possible, yeah, use triaxial testing. But for recompacted soils, when you've got a lot of air in the samples, and I'll talk a bit more about this in our next webinar, it can give you all sorts of issues in ensuring saturation and so on. So yes, use triaxial if you can do it, but if it's difficult, then shear box is perfectly satisfactory. You probably get a slightly lower strength from the shear box, but there's no harm in that. Right, hang on, let me just go to the next one here. In the first part of your presentation, you mentioned that geotechnology in the region usually uses this test for fill soil. Yeah, okay. My question is, there any way to tamp the sand properly in the shear box so that it represents the expected density of soil fill in the field? Yeah, that is something that you can do. Laboratories will tend to develop their own techniques of tamping it. So if you take the first example I showed you, that was a dry sand, and it was prepared fairly densely. And then later on, I had that example with the dry sand test where you had both loose and dense. And that was all done by careful preparation. So probably to get the loose state, you simply pour the sand in very carefully and you don't do anything to it. But to get the dense result, you're going to use either some simple tamping device or maybe a vibration device. There are various techniques for doing it. If you struggle to get the density that you expect in the field, then you're going to have to add water. And then you're going to get into the issues with saturation and so on. But very important point asked there. So now we have a next question. Right. Between peak and CV strength, which one of these results that we should use and which is, I guess, relevant? Well, this will tend to depend on your design requirements and procedures. If I think about reinforced soil design, which is the area I work in mainly, then when it comes to the choice, it's normally given to you in the design method. So there are some reinforced soil design methods that tell you to use FICE, and there are others that tell you to use FICE. Now, of course, using FICE is on the safe side because it's the lowest likely strength. But in some situations, that's not a bad thing. But again, you really need it's really to take into account the advice that you see in different design codes and so on. So it's quite a big topic. I mean, maybe in a future webinar where we look more at application of this information, I might come back to that particular point. Also, of course, perhaps one last thing to mention on that one is that the FICE is incredibly reliable. You can't go far wrong with FICE. FICE, because you've got to get the right compaction and so forth, you can get a wide variety of answers, as we saw in some of those examples. How to get undrained shear strength based on direct shear box tests, given that there are limitations. Yeah, I really don't recommend you try and measure the undrained shear strength of a clay soil in the shear box. If your sampling is excellent, and if you get the sample, normally you're going to use the circular shear box, which I didn't show earlier on, but there's also a circular option to take samples straight out of sampling tubes. Then if you're really good and you get the sample in there quickly and you do your test very quickly, you might get a reasonably representative result. But personally, I would rather determine undrained shear strength in the triaxial test because I think it's going to be more reliable. So probably not the best idea. If you do an unconsolidated fast shear box test on a clay sample, you might get something approaching the undrained shear strength. But I think on the whole, it's going to be on the low side. We saw that actually in one or two of those examples I showed you earlier on. Let me just have a look. Here we go. We have a question here about products to be used for repairing slope failures. Well, kind of outside the scope of this webinar today, maybe we could talk briefly about the soils to be used in repair of failures. And the answer is you can use a wide range of soils in repairing landslides. But of course, you've got to make sure that they are well recompacted in a good condition, a good state. You don't want very wet soils. And also, if you have a landslide that has created a shear plane, say in a clay particularly, or a fine soil, then you don't want to leave it in there. So it's really important you identify the location of that, and you can then excavate the soil. You may even reuse it, but you'd have to completely break it up, remold it, and get rid of any effect of that shear plane. Now here's one. Have you used this for whether instruments or supporting tools such as generally these days all shear box testing is done with remotely controlled measurement devices. So in the good old days we'd use proving rings and dial gauges. They still get used, but then you have to manually read them. With modern equipment, you're probably going to use transducers, but to measure both load and the displacements. And of course, that's nice because you don't have to have a technician standing there taking readings all the time, and probably a bit more accurate, but it costs more money. So I think many laboratories these days are still going to be using the good old dial gauge approach, because the proving ring has a dial gauge, and then you've got 2 displacement dial gauges. So it's 3 dial gauges you're reading as the test goes on. Anthony Gunawan, yes, of course. Right, I would like to ask the following. The time to failure. 50 times T50, 11.6 times T90, and 12.7 times T100. How come the time taken for T100 increases? No, this is not quite the way. What we're trying to do here is to calculate the required time to failure. So yes, you're right, 12.7 is a greater number. I'd have to say that that came from the head book. Yes, you're right. There isn't a big difference. The 11.6 times T90 comes from the ASTM, but in the method of analysis, which I didn't put on the diagram because it would have gotten a bit messy, you actually you move the line forwards by a ratio of, I think it's 1.15 to get to the T90. So because of those methods of the way you draw the diagrams, T90 could actually be higher than T100. I know that doesn't quite make sense, but it's all to do with the construction that you use when you look at the settlement versus time plots. No, it's a good spot. Well spotted that. I mean, it doesn't look right, I agree. But in reality, it's unlikely because of the way we calculate T90 would actually be higher than T100 if you follow the code recommendations. These are all numbers coming out of codes of practice, and they're not based on looking at consolidation theory. There's sorts of numbers we find in codes of practice. But good question. No, thank you for pointing that out and reminding me, giving you a chance to explain it. Oh, we have a local question here. Can we determine undrained residual strength parameters? Can you use the ring shear? Yeah, that's a good question, that. When we look at residual strength, we're not really interested in the undrained. We're only really interested in drain. We want to find out the phi dash residual. And to do that, we don't normally use a shear box. You can try. And in fact, there are procedures where you have to keep reversing the shear box. So you run it in one direction, then you turn it around, you run it back the other way, and so on. So it's not perfect. It's not too bad if you really are trying to find this, but ideal is to use what's called the ring shear apparatus. Now, I don't think you'll find many laboratories in Indonesia with a ring shear. I don't know, maybe some of the universities have got them. But in the ring shear apparatus, it literally is that. You have a ring of soil, so you spin the thing around in a circle. So you have continuous shear in one direction. The original idea is really invented in Imperial College. People like Skempton and Bishop heavily involved with that. Professor Bishop developed a rather difficult to use residual shear, ring shear apparatus, which required that you cut out an undisturbed sample in an annular shape, which is difficult. And then another gentleman called Bromhead, he developed a much simpler apparatus where you simply test the material remolded. Because to be honest, by the time it's reached its residual strength, it doesn't really matter whether it started off life as undisturbed or remolded. Now, another question here. I've seen a lot of those high C, low phi results for silty, sandy, and sandy silt soils. The problem is the shearing rate is rarely mentioned in the lab results. Yes, I know, especially in Indonesia. Even sometimes the vertical versus horizontal basis curve is not there. I'm just curious. Do you happen to request them up front when requesting the direct shear test? Right, well, this is a very good question. If the laboratory is following the standards, then all of this information should be provided. Certainly the ASTM has a very thorough list of information, and so does the SNI. So if the laboratory is not providing all of that information, then I'm afraid they're not fulfilling the requirements of the test standard. And of course, if you are specifying, if you are getting a test done on, say, behalf of a client who's paying for it, then maybe you should make sure that it's made very clear that you require that the full information is provided as per the standard. Get hold of the standards. At the end of each one, there's a long list of the required information which should be provided. And really important that it is done completely. That's why on some of my example results. I left the diagrams complete, but I left off the information because it hadn't been presented. And this one about the vertical movement of the shear box is really important, especially in the granular soils. So if you're trying to interpret shear box testing in granular soils and you don't have the vertical movement of the shear box, then it becomes difficult. Also, sometimes I have seen test results where I'm pretty sure the laboratory has actually given the results the wrong way around. In other words, they've reported upward movement as downward movement. I think I've seen it in some tests. In other words, I've seen tests on coarse soils with 5 values of 45 degrees, and apparently the shear box is going down. It's simply not possible. It must be dilating for such a high 5 value. So it's a good question, this, and I think also almost one of the most important ones. And it goes back to what I said at the beginning. You really need to get all the information you can. Everything should be there to allow you to assess a test result. And don't be shy, don't be malu to reject a test. It's difficult because if you get a test specified by somebody else and you think it's wrong, then you're going to have to say something about it. I think it's very dangerous to be forced into using high C, low phi in, say, the design of a reinforced soil structure or simply a fill slope, because especially at low stresses, you're going to have much too high a shear strength. And this is very dangerous because the high C dashed, what does that do? At low overburden pressures, it gives you a high shear resistance, which may not be there. So please be very, very careful. Look out for the high C, low phi. I see it more often than I don't when in tests on fine soils. I think that's pretty well all the questions. There are 9 of them. If anybody else wants to add a question or two, we've probably got a few minutes. Otherwise, there's something on the chat. I'm not quite sure. I better have a look at that just to make sure the chat doesn't tell me something I need to know. No, okay, right. So unless there's any other question, I think that brings, unless the organizers can tell me there's another question that I've possibly missed. I think they're all answered now. There are still 9 of them. So I'd like to thank you, actually. First of all, you wrote them all in English, which obviously is a bit quicker for me to read. Those were all good questions. And I think they all complemented very much the material that's in the webinar. Of course, you will be receiving a PDF copy of all of the slides. As I mentioned earlier on, I shall add a few more references, which I think are useful to have. I've just seen a number 10 question arriving. So let me just see. What is the physical explanation of the increase in friction angle of silty sand with increased water content when direct shear test is performed? Now, this is a good question. In fact, the friction angle will not be affected by the water content, assuming the density is always the same. Don't think that because there's water in there, it kind of makes the soil particles more slippery. It's not the way. But the issue with having a water content in there, especially if you do the test a bit on the far side, is that you may well create suction. And then when you plot your shear stress versus normal stress, your normal stresses won't be effective stresses, they'll be total stresses. And if you remember, I had that example where I added the effective stress result to the total stress result, and I showed those suction values. And it looks like it could be stronger. Would it be a higher friction angle? Possibly. It just depends on the nature. It normally ends up with the high C value and possibly a lower friction angle. But certainly it ends up with a higher shear strength. And that's the issue. Be very careful with high C, low phi. 11, one more question. The organizers might stop me in a minute, but let's see what number 11 is. How do we find the Young's modulus from direct shear testing? You cannot. It's simple, that we do not measure stiffness. And that's why, as I mentioned earlier on, there's a bit of a danger if laboratories plot the horizontal displacement as a strain. You might think you're measuring a stiffness, but there is no stiffness measured. You might get an indication of the consolidation properties from the consolidation stage for clays, but in terms of real stiffness, no, you're not measuring it, so you can't get it from a shear box test. It's one of the things you don't get. We have number 12 now. I noticed in some shear box test results presentation from the soil lab that X and Y axis shear is not using the same scale. Ah, right. Yes, that's often the case. I know, because laboratories are often using things like Excel or other programs to plot their diagrams of shear stress versus normal stress, then sometimes they won't have the same scale. So it's okay, but you've got to realize it looks wrong. For me, I carefully, in all my diagrams, I carefully made sure that the normal stress and the shear stress had the same scale. So in other words, the squares are square on the diagram because they always have the same values on the intermediate points. So I think to help you get the right impression of the test, it's really helpful if the scales are the same on the shear and normal stress axes. And if they're not, it doesn't really matter. You should still get the same answers as long as you calculate things from the values and you don't measure them with a protractor or something, which we don't do anymore. But yeah, so it's okay, but it's just not helpful. So easy to do it correctly. But that's an interesting comment that people have noticed that. I've noticed it too. Okay, organizers, how are we doing? You're going to have to tell me. Committee, we've reached all questions now. We covered all questions. I'd like to thank you some, again, furthermore, very good. The question about the stiffness modulus measuring is really important. No, we cannot get it. I'll just repeat that. We cannot get stiffness or modulus from a shear box test. Right.
Oke Pak Mike, terima kasih sekali lagi atas waktu dan paparan serta jawaban yang diberikan. Bapak, Ibu, dan rekan-rekan sekalian, kita akan beralih ke sesi selanjutnya, yaitu kuis berhadiah. Kuis berhadiah ini akan dipandu oleh Riva. Kepada Riva, dipersilakan ya.
Oke, terima kasih Mbak Wira. Halo dan selamat siang kepada Bapak, Ibu, dan rekan-rekan mahasiswa yang hadir hari ini. Perkenalkan, saya Riva yang akan memandu jalannya games pada kali ini. Sebelum kita mulai, saya akan berikan tata cara bermain 50.000 untuk 3 orang pemenang hari ini. Silahkan diperhatikan di screen yang sudah saya bagikan. Kita punya hadiah uang tunai untuk 3 orang pemenang. Sekarang Bapak, Ibu, dan rekan-rekan mahasiswa, silahkan buka browser Anda, baik di PC maupun di handphone Anda. Silahkan buka browser Anda, kemudian ketikkan menti.com. Setelah masuk ke menti.com, 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 maka masukkan kode angka yang diberikan. Kodenya adalah 3330839. Sekali lagi, kodenya adalah 3330839. Buka browser Anda, boleh lewat PC, boleh lewat komputer, boleh lewat handphone langsung, kemudian ketikkan menti.com dan masukkan kode 3330839. Kemudian masukkan nama Anda, tolong namanya dimasukkan sesuai dengan nama yang Anda registrasikan saat mendaftar Zoom webinar ini. Kalau lupa daftarnya pakai nama apa, silahkan dilihat di display name yang Anda gunakan untuk masuk ke Zoom sekarang. Itu namanya sesuai dengan nama yang Anda registrasikan di halaman registrasi di awal. Silahkan ke menti.com, kemudian masuk 8319, kemudian isikan nama Anda. Kita akan tunggu sampai beberapa peserta lain masuk. Hadiahnya adalah total 450.000 untuk 3 orang pemenang. Juara 1 akan mendapatkan Rp200.000, juara 2 akan mendapatkan Rp150.000, dan juara ketiga akan mendapatkan hadiah sebesar Rp100.000, totalnya Rp450.000. Ayo kita main games. Masih tunggu beberapa peserta lagi. Kita ganti, kita lihat ke games, kita lihat sudah berapa yang join. Kita ada 99 orang yang join, masih ditunggu sekitar 2 menit lagi, 102 orang. Ayo masukkan di browser Anda menti.com, kemudian masukkan masukkan kode yang sudah diketikkan juga di chat box. Kemudian masukkan nama Anda dan kita akan bermain. Pertanyaannya ada 3, semuanya sesuai dengan apa yang sudah disampaikan dalam presentasi Pak Michael Dobie, karena 3 pertanyaan ini dibuat langsung oleh Pak Michael Dobie. Pertanyaannya dalam bahasa Inggris. Gimana cara menangnya? Cara menangnya adalah Anda harus jawab dengan benar, tapi tidak hanya benar, harus cepat. Jadi pastikan koneksi internet Anda stabil, sehingga nanti tidak kalah cepat dari peserta yang lainnya. Masukkan menti.com, kemudian masukkan kode yang sudah dimasukkan di chat box, dan masukkan nama Anda sesuai dengan registrasi. Kita masih tunggu 30 detik lagi ya. 114 orang yang sudah join. Masih ditunggu, apakah masih ada lagi yang mau ikut? Hadiahnya 450.000 totalnya. Juara 1 mendapatkan Rp200.000, juara 2 Rp150.000, dan juara 3 mendapatkan Rp100.000. Cuman 3 pertanyaan. Kodenya 33308319. Kodenya 33308319. Masukkan nama sesuai yang Anda registrasikan. Kalau lupa, lihat di display name yang ada di Zoom yang Anda gunakan saat ini. Oke, kita hitung mundur ya. 20 detik, 20, 19, 18, 17, 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Kita akan bermain dengan 120 peserta. Pertanyaan pertama. Siap-siap, pastikan internetnya stabil. Pertanyaan pertama, jawab cepat untuk mendapatkan poin lebih banyak. A shear box test on clay has results C is equals to 35 kilopascals and phi 13 degrees. For design of a field slope, do you A, reject the result, or you accept the result and use it in your analysis, or try to find the full test result and investigate the method used? Waktu Anda 40 detik dari sekarang, pastikan Anda menjawab dengan benar dan cepat. Ayo. A shear box test on clay has results C equals to 35 kilopascals and phi equals to 13 degrees. For design of a field slope, do you reject the result? Do you accept the result and use it in your analysis? Or you try to find the full test results and investigate the method used? Waktu Anda 10 detik lagi. 3, 2, 1. Baik, jawabannya adalah try to find the full test result and investigate the method used. Ada 48 orang yang benar. Kita lihat di pertanyaan ini siapa yang memimpin klasemen. Tapi belum tentu menang ya. Yang jawaban yang tercepat di akhir nanti itu adalah pemenangnya 3 orang. Bukan yang ini, tapi kita lihat dulu siapa pemimpinnya. Siapa kira-kira? Ya, yang tercepat adalah Rosi Elfri Alawiyah. Kita lanjut, pertanyaan kedua, masih bisa mengejar yang lain dengan menjawab dengan cepat dan tepat. Kita masuk ke pertanyaan kedua. Question 2 of 3. Answer fast to get more points. You are planning site investigation for a clay fill embankment, including shear box test. Local standards have 3 methods. Which one do you use? Do you use consolidated fast shear at 250 USD per test, or you use unconsolidated fast shear at 150 USD per test, or consolidated slow shear at 1,000 USD per test? You have 35 seconds to answer the question. Silakan, waktu Anda 20 detik lagi. Pertanyaannya, you are planning site investigation for a clay fill embankment including shear box test. Local standards have 3 methods. Which one do you use? Yang pertama, yang kedua, atau yang ketiga? Waktu Anda 10 detik lagi. Kita lihat siapa yang memimpin di pertanyaan kedua ini. 3, 2, 1, waktunya habis. Kita lihat siapa yang memimpin di pertanyaan kedua, tapi belum tentu menang. Yang lain masih bisa mengejar. Yang tercepat adalah Tubagus Ferry, tapi yang memimpin leaderboard di pertanyaan kedua adalah Antoni Gunawan. Kita masuk ke pertanyaan ketiga. Pertanyaan terakhir, pastikan internet Anda siapa 3 orang pemenang yang mendapatkan hadiah total 450.000. Question 3 of 3. Answer fast to get more points. You are designing a major retaining wall project with a source of well-graded sandy gravel fill. The laboratory has 3 shear box sizes available. Which do you specify? First choice is 60 millimeters at 150 USD per test, or 100 millimeter at 250 USD per test, or 300 millimeter at 1,000 USD per test. Silakan dijawab waktu Anda 40 detik dari sekarang. Waktu Anda 20 detik, apakah yang pertama, atau yang kedua, atau yang ketiga? Kita hitung mundur, sudah 10 detik lagi. 6, 5, 4, 3, 2, 1. Waktunya habis. Hasil yang sekarang menang, itu adalah pemenangnya. 3 orang teratas. Ya, kita lihat siapa. 34 orang yang menjawab benar, yang menjawab salah lebih banyak. Kenapa? Tapi oke, kita lanjut. Siapakah yang memenangkan hadiah total Rp450.000? Kita lihat. Selamat kepada Edwin Lee sebagai pemenang juara pertama dengan poin 2.884, berhak mendapatkan hadiah Rp200.000. Kemudian di posisi kedua dengan total poin 2.882 adalah Bapak Antoni Gunawan. Kemudian di juara ketiga yang mendapatkan Rp100.000 adalah Nina Yuliana dengan poin 2.876. Selamat kepada 3 pemenang, Pak Edwin, Pak Antoni, dan Ibu Nina. Kuis dan hadiah ini dipersembahkan PT Multibangun Rekatama Patria Geosintetik Spesialis. Baik, saya berikan kembali kepada Mbak Wira. Terima kasih semuanya. Silakan Mbak Wira.
Baiklah, terima kasih Rifa yang sudah memandu acara games berhadiah pada pagi hari ini. Dan selamat kepada para pemenang. Dengan berakhirnya games tadi, maka sudah sampailah kita di penghujung acara. Kami mengajak Anda untuk mengikuti MRP Webinar Series selanjutnya pada tanggal 8 April 2021 jam 10 waktu Indonesia Barat dengan tema The Principle of Effective Stress and Measuring Soil Strength Using the Triaxial Test. Anda dapat langsung mendaftarkan diri di link s.id/id di webinar MRP3. Untuk informasi mengenai sertifikat dapat diakses melalui link s.id/mrpweb2 yang juga tertera pada kolom chat atau yang tertera pada layar Anda. Apabila Anda memiliki pertanyaan atau terdapat kesalahan penulisan nama pada sertifikat Anda, silakan hubungi Rifa melalui WhatsApp di 0822 9851 0700. Untuk informasi lebih lanjut terkait PT Multibangun Rekatama Patria dan acara-acara kami selanjutnya, silakan ikuti media sosial kami. Akhir kata, kami mengucapkan terima kasih kepada seluruh peserta, pembicara, dan panitia yang terlibat dalam acara ini. Kami juga memohon maaf jika terdapat kesalahan dan perbuatan selama acara berlangsung. Kami menunggu Anda di MRP Webinar Series selanjutnya di bulan depan. Sampai jumpa dan selamat siang.
Yang pertama, segmental retaining wall system terpanjang di Indonesia. Multiple retaining wall system pada jalur kereta api Batu Ceper Tangerang ke Bandara Soekarno-Hatta. Konstruksi ini memiliki panjang 2,4 km. Yang kedua, jembatan terpanjang di Indonesia yaitu jembatan Suramadu, Surabaya Madura yang berada di Jawa Timur. Jembatan ini memiliki panjang 5,4 km. Yang ketiga adalah bendungan terluas, yaitu Bendungan Jatiluhur yang berada di Jawa Barat memiliki luas 8.300 hektar. Dan yang keempat adalah gedung tertinggi, yaitu Gedung Gama berada di Jakarta setinggi 310 meter. Dan yang terakhir adalah peninggalan sejarah termegah, yaitu Candi Borobudur. Candi ini memiliki luas 2.500 meter persegi dan tinggi 35 meter. Gimana? Menarik?
Halo Sobat Multibangun, di video kali ini kita akan bahas jenis-jenis geosintetik. Persatu, geosintetik adalah bahan tiruan atau sintetik yang digunakan dalam proyek konstruksi yang berhubungan dengan tanah atau batuan. Di video kali ini akan kita bahas adalah geogrid dan geotekstil. Geogrid adalah bahan geosintetik yang berupa lembaran dan memiliki bukaan. Ada triaxial dan uniaxial. Geogrid triaxial adalah bahan geosintetik yang memiliki bukaan berbentuk segitiga yang seperti ini. Fungsinya sebagai stabilisasi tanah dasar yang lunak pada proyek jalan dan area penumpukan. Geogrid uniaxial adalah bahan geosintetik yang memiliki bukaan memanjang satu arah yang seperti ini. Fungsinya adalah untuk perkuatan timbunan tanah atau lereng. Selanjutnya geotekstil. Geotekstil adalah bahan geosintetik berpori yang memiliki sifat tembus air. Ada woven dan non-woven. Pembahasan selanjutnya tunggu di part 2 ya. Sampai jumpa.
Halo Sobat Multibangun, kali ini kita masih akan bahas jenis-jenis geosintetik. Part 2. Kemarin kita sudah bahas geogrid nih. Sekarang kita bahas geotekstil. Geotekstil adalah geosintetik berpori yang memiliki sifat tembus air. Ada geotekstil woven, ada geotekstil non-woven. Geotekstil woven, geotekstil yang teranyam, ya, terpal tuh. Fungsinya sebagai separator atau pemisah lapisan material. Selanjutnya geotekstil non-woven, geotekstil yang tidak teranyam seperti karpet. Fungsinya sebagai penyaring lapisan material tanah. Gimana? Udah tahukah tentang geotekstil? Part selanjutnya kita akan bahas geomembran. Ditunggu ya.
Halo Sobat Multibangun, di video kali ini kita akan bahas jenis-jenis geosintetik part 3. Di video sebelumnya kita udah bahas tentang geotekstil. Nah, di video kali ini kita akan bahas tentang geomembran. Geomembran adalah geosintetik yang memiliki sifat kedap atau tidak tembus cairan. Fungsinya adalah mencegah cairan masuk ke dalam tanah atau menembus material tertentu. Geomembran biasanya digunakan untuk embung atau kolam penampungan air, kolam limbah, tambak udang, dan tempat pembuangan sampah akhir atau TPA. Sekarang udah pada tahu kan tentang geomembran? Tunggu video-video kita selanjutnya ya. Hei, pada serius amat. Gombalan teknik sipil cek. Mas Andi, gombalin dong.
Kamu punya teodolit nggak?
Buat apaan?
Karena aku mau mengeker atau melihat perasaanmu padaku.
Mbak Astri, gombalin juga dong.
Sekokoh-kokohnya pondasi tiang panjang, lebih kokoh cintaku padamu.
Mas Bagus, gombalin juga dong.
Kamu lulusan teknik sipil ya?
Kok tahu?
Iya, karena kamu berhasil membuat jembatan hati antara aku dan kamu.
Mbak Wira juga dong.
Berbulan-bulan di proyek, aku sanggup. Gimana kalau cuma menunggu kepastian kamu?
Patri, gombalin dong.
Jalan dan gedung aja aku bangun, apalagi membangun rumah tangga dengan kamu.
Pak Jamal, ayo.
Aku nggak bisa kembali.
Ya, Pak Mamo deh.
Udah terbukti.
Halo Sobat Multibangun, di video kali ini kita akan bahas istilah-istilah pada konsepsi flyover. Flyover atau jembatan layang adalah jalan yang dibangun di atas kawasan atau jalan atau jalur kereta api atau persimpangan jalan untuk menghindari kemacetan lalu lintas. Nah, ini nih bagian-bagian dari konstruksi flyover. Nah, yang ini namanya abutment, fungsinya untuk menopang jembatan di bagian ujung-ujung jembatan. Oprit jembatan atau jembatan pendekat adalah timbunan tanah atau urukan di belakang abutment. Ini girder, struktur horizontal yang menopang bagian utama jembatan. Ini adalah pier, struktur vertikal yang menopang girder jembatan. Ini dinding penahan tanah, yaitu dinding penahan timbunan tanah di bagian oprit flyover. Tiang panjang atau bore pile adalah struktur di dalam tanah yang menahan jembatan.
Halo Sobat Multibangun, video kali ini kita akan membahas perbedaan antara insinyur sipil dan insinyur arsitek. Insinyur sipil menghitung kekuatan bangunan. Insinyur arsitek mendesain keindahan bangunan. Insinyur sipil mendesain sarana dan prasarana seperti jalanan dan jembatan. Insinyur arsitek mendesain tata kota. Insinyur sipil harus mahir menghitung. Insinyur arsitek harus mahir seni menggambar. Insinyur sipil tidak harus paham warna. Insinyur arsitek harus paham warna. Kalau insinyur sipil bisa jadi konsultan atau kontraktor. Insinyur arsitek biasanya jadi konsultan perencana. Bagaimana? Udah tahu kan perbedaan antara insinyur sipil sama insinyur arsitek? Sampai jumpa!
Halo Sobat Multibangun, di video kali ini kita akan membahas alat pelindung diri yang ada di proyek. Yang pertama, helm proyek. Kayak video yang kemarin, jangan lupa dicek ya. Fungsinya untuk melindungi kepala kita dari benda yang jatuh dari atas. Walaupun AC ini jangan digunakan untuk naik motor ya, karena itu nggak aman. Yang kedua, safety shoes. Fungsinya sebagai pengaman pada tempat berlumpur atau becek. Juga mencegah kecelakaan fatal pada kaki. Selanjutnya, rompi proyek. Ia memiliki material retroreflektif agar mudah terlihat di lokasi proyek, terutama di malam hari. Berikutnya, sarung tangan. Fungsinya untuk melindungi tangan dari kecelakaan kerja seperti terpotong, tertusuk, dan terjepit. Selanjutnya, kacamata safety. Fungsinya melindungi mata dari debu dan partikel-partikel kecil yang berbahaya. Dan yang terakhir, body harness, biar tidak terjatuh. Nah, jangan lupa pakai APD ya.
Halo Sobat Multibangun, udah pada tahu belum? Ada dua jenis pekerjaan teknik sipil, konsultan dan kontraktor. Cari tahu yuk perbedaannya. Konsultan kerjanya menghitung dan mendesain proyek serta mengawasi proyek. Kalau kontraktor